Hello everyone, I'm Wei Du. Today I'm introducing you to the multi-resolution A-star algorithm. This research is conducted with Farhan Islam and my advisor Maxim Likachev from the Search-Based Motion Planning Lab at Carnegie Mellon University. The completeness and efficiency of search depends dramatically on the size of the discretization. Assume we have a point robot which always lies at the center of cells. On the left of figure A map is discretized into two resolutions, and expanded units are marked in blue. A coarse discretization is taking the narrow passage as infeasible, and hence search expanded the first row and exited. However, a finer discretization on the right recognized the path through the narrow passage. Figure B shows a cul-de-sac. On the left is a coarser resolution map where planar only takes 4 expansions to escape the local minima. On the right, planar takes around 100 expansions before it can exit the cul-de-sac. These two cases show that coarser resolution leads to faster search but potential incompleteness. Finer resolution leads to stronger completeness but slower search. So we are wondering, why not use different resolutions at different places of the map? The most related works are methods regarding adaptive resolutions or multiple levels of hierarchies as listed above. One famous algorithm is the party game algorithm, which iteratively divides the near-obstacle region into higher resolution every time it fails to find a solution. The other type of algorithm is searching in hierarchical structures, such as chord tree data structures. These algorithms perform well on sparse environments when it comes to highly occupied environment. They perform even worse than searching on a high-resolution map. These algorithms will eventually reach a high resolution with extra computation costs such as bookkeeping the relative positions between cells. Apart from that, these algorithms cannot be easily scaled to high-dimensional planning problems. In these problems, MRI-star has the advantage of planning with different resolutions without constructing the mapped structures mentioned above. The key idea of multi-resolution A-star is simple, which is searching along each resolution at the same time, while sharing partial solutions found. Here is how partial solutions are shared. We have a map discretized into two resolutions in gray and yellow respectively. In figure A, state S0 in high resolution space is expanded and states S1, 2, 3 are generated and inserted into high resolution space Q1. Since state S2 also lies at the center of a coarser resolution unit, it will also be inserted into low resolution space Q2. In figure B, we expand state S2 from a coarse resolution space, and successors S4 and S5 are generated. Since S4 and 5 also lie at the center of a fine cell unit, they are also inserted into high resolution space as well. Hence, coincided states are shared between searches. And furthermore, segments of paths are shared. This is similar to state sharing in alternation method and multi-heuristic A-star. So this is the process of multi-resolution A-star, which is trivial to implement. It can also automatically figure out when part of a solution has to lie on the finer resolution and when the local minimum can be filled on a coarser resolution. Besides, it can provide completeness and bound suboptimality with respect to a user-specified resolution referred as an anchor resolution. Here is a simple example of how this algorithm works on a 4-connected grid map. This time, we have two resolutions in gray and orange, respectively. The heuristic is Manhattan distance. In figure A, the search started at state A2. In figure B, A1, B2, and A3 are produced as successors of A2. They are inserted into high-resolution queue. Apart from that, B2 is also inserted into low-resolution queue. In figure C, state B2 is expanded, its successor E2 is generated and inserted into both Q1 and Q2. As the search continues like this and reaches goal state, in figure G, a solution is found and composed of segments from different spaces, as you can find in red and purple. This is benefited from sharing the states. The MR star search follows the structure presented here. Assuming the domain is discretized into multiple resolutions indexed from 0 to n, then we run weighted A star search in each resolution space from 1 to n. In addition, we have an anchor search, which is an optimal search running with resolution 0. The inequality on the right is used to control the inadmissible expansions with respect to anchor search. Then we compare the key 0 from anchor space with key I from search I. If the anchor condition is satisfied, a state will be expanded from the ith search, otherwise anchor search. Furthermore, we have a scheduling policy to decide from which search to expand states. The scheduling policy can be round-robin style or dynamic Thompson sampling, etc. In the end, MR star stops when goal is found by any search or when null spaces are exhausted. Here are the properties of MR star. Firstly, since MR star only expands a state once in one space, then theorem 1 holds. Secondly, the search stops when the solution is found or all spaces are exhausted, so it is complete in the union space of all resolutions. At last, since all searches are controlled by the anchor condition, the solution cost from any search is bounded as in theorem 3. The details of the proof are presented in the paper. Resolutions should be selected to largely overlap the spaces so as to facilitate sharing. The size of a coarser resolution could be multiples of the size of a finer resolution. Hence, the center of a low resolution unit will always coincide with the higher resolution unit. On the first row of the figure, the map have resolutions at 4 meters and 12 meters, so there are states such as S2, S4 are overlapped between different spaces and thus shared. On the second row of the figure, when the map is discretized with 3 meters and 5 meters resolution, there will rarely be transitions between two resolution spaces, because states like S0 will largely exist in high resolution space, whereas S1 will only exist in low resolution space. Then, how do we select the resolutions for anchor search? There are 3 types of choices. The first is using the highest resolution. It can provide tighter optimality bound than mid-level resolutions, because the optimal solution on higher resolution map is more similar to the real optimal solution. Also, in the anchor search, we only consider the set of actions that could be used in high resolution space. However, when the anchor space is exhausted, there will not be any bounds for the solution found later. We can also choose the mid-level resolution. Then the anchor search will march faster because of larger step size, and anchor search will only consider the set of actions required in mid-level resolutions. But similar to using high-level resolution, there will be no bounds for the solutions when anchor search exhausted. And compared to high resolution space, the optimality bound will be looser. To always provide suboptimality bounds for the search, we can choose the union of all resolutions as anchor resolution. It will always provide bounds because union space is the last space to be exhausted among all spaces. On the other hand, the search in union space will require actions in all resolutions, which increases the branching factor as well as the computation load. Here are experiment results. The performance of planners are evaluated in terms of success rate, planning time, and mean cost. Firstly, we implemented the algorithm on 2D maps. The map size is 10,000 by 10,000, and we have resolutions in 1 meter, 7 meters, and 21 meters. We have baseline algorithms weighted A star searching on a single graph combining all resolutions, denoted as weighted A star MR, in highest resolution, denoted as weighted A star high, and lowest resolution, weighted A star low. Besides, we have implemented called tree search, denoted as QD tree. Baseline algorithms are using weight as W2, so all algorithms have the same bound. As you can find on table 1, In both maps, MRI star consistently have highest success rates. In terms of mean planning time, it only runs slower than weighted A star in low resolution and college research. However, weighted A star in low resolution is not complete and thus failed a lot. College research is implemented on an explicit graph, which is previewed and saved the time of constructing new states during planning, but the precomputation cost is around 9 seconds on these large maps. And then we conducted our experiments using a PR2 rubber arm in 4 scenes: kitchen, bookshelf, industrial, narrow passage. The angular resolutions for each joint are discretized into 3 degrees, 9 degrees, and 27 degrees. The results for each planning scene are documented separately. The baseline algorithms are weighted A star search on a single graph combining all resolutions, weighted A star search with adaptive dimensionalities, RT Connect, and RT star given a 120-second time limit. In terms of success rate, MRI star consistently have high success rates in all scenes. Besides, MRI star is faster than other search-based algorithms and RT star for most of the time. Although it is not as fast as RT Connect, the solution quality from MRI star is much better than RT Connect, and even better than RT star. The improvements shown below is consistent with the results from 2D planning. There is a significant improvement in planning speed, but not that much improvement in cost. To conclude, we proposed MRI star algorithm for planning tasks in large state space. MRI star obtains fast planning speed by searching multiple resolution spaces and sharing partial solutions between them. And we have presented that MRI star is complete in the union search space and could also provide solutions with bounded quality. Although MRI star performs well in most of the test cases, there are still some interesting areas to be explored. For example, it is worth trying to incorporate a multi-resolution A-star framework for other bounded suboptimal search algorithms, or applying MRI star to high-dimensional kinodynamic planning. In the end, thank you for attending my presentation.